All right, so we're going to be working on a new skill today. Something a little bit we saw last time, but we're going to focus, kind of drill down on one specific thing from last time. So last time we were together, we were looking at two different things. We were looking at equations and expressions, right? Remember we said expressions were, let's go back to our notes from yesterday, said expressions were something with numbers, variables, and operations, right? So that would be 3n plus 1 or 2 plus 2. And we said equations are specifically expressions that show a math relationship. So 2 plus 2 equals 4, or 3n plus 1 equals 5n, or x equals 4. We said specifically that equations have an equal sign. And we saw a lot of different types of equations last time and wrote some of our own. So we're going to be looking today at a very specific kind of equation. We're going to be looking at a specific type of an equation oftentimes called a rate equation, R-A-T-E, that has this form: y equals mx. Now, to be really specific, these letters stand for specific things, right? So for example, so y and x are variables. And m, in this case, is a number. So y equals mx, this definition up here, is the kind of form, right? It's like the general case. So what I mean by that is it doesn't have to be y, it doesn't have to be x, and it won't be m, but they're in this kind of shape. So I'll give you some examples here. So there are a few examples that are in your CMP book that are also on the activity in Desmos. Let's look at this one here. C equals 21n. So you'll see, just like our example up here, it has two variables. One variable, it has one variable equals a number times another variable. So this specific type of equation has variable equals a number times a variable. And I'm going to use that dot symbol to mean times a variable. So C equals 21n is one example, right? We have a variable equals a number times another variable. We see also that T equals 0.06p is another example. We have a number times a variable equals another variable. So 0.06 times p equals t, or 21 multiplied by n equals c in that first one. And we have a third example here. D is equal to 20 times t. So one variable is equal to another variable times a number. So that's the kind of equation that we're going to be looking at. They're sometimes called rate equations. That have this form y equals mx plus b, or y equals mx rather. All right, so I want to kind of zoom in on a couple key ideas about this that are going to be really helpful for today. So we said yesterday that if there's a number in front of a variable, I'm actually just going to take this and I'm going to copy and paste from up here so that I don't have to rewrite all of it. So we said before that if there's a number being multiplied by a variable, like right here, We have a number that's being multiplied by a variable. If there's a number being multiplied by a variable, we call that number the coefficient, right? So instead of writing number here, I'm going to put coefficient underneath it so that we remember that that's what we call a number being multiplied by a variable, a coefficient. So when we see an equation like this, where it's one variable being multiplied by a number to get another variable, when we see an equation like y equals mx, like this, this coefficient has a special meaning. M, which we say is the coefficient, tells us the rate, so we call this the rate of change. And what we mean by the rate of change is it tells us how much one variable changes when the other one changes. So I'll give you a couple examples here. Let's pull down a couple of our examples. Let's pull down this one specifically for now. So here's an example. I'm going to put a little example next to it. So in this example, C is cost, N is the number of customers, and 21, right, 21 here is our coefficient, right? Because 21 is the number that's being multiplied by a variable. So 21 is our coefficient. In this case, because it's a rate equation, right, because it's a variable times a number equals another variable, this 21 is our rate of change. Because it tells us how much the cost changes when we change the number of customers. Right? So for example, in this case, we say that 21 is the price per customer, right? Because if I have, let's take an example here, I'm just going to use a different color. If I had one customer, so if n is equal to 1, my cost would be $21, right? Because N tells us what the cost is for a certain amount of customers, right? So N tells us the price per customer. So if there's one customer, it's $21. If we were to change M, if we were to change that 21, let's say I made a fake equation like this. I said C equals 11N. That would change the price per customer, right? That would mean that if I had one customer, my cost would be $11 instead of 21, right? So that number in front of the variable, right, the coefficient, the rate of change, tells us how much one variable is going to change the other. Let's just go through two more examples before we look at the problems we're going to do today. So let's look at this example here. So we have t is equal to 0.06 times p. So our coefficient is 0.06. So 0.06 is our rate of change. So 0.06 tells us that if I make one more dollar, if P goes up by 1, right, that means t is going to go up by 0.06 times 1, or 0.06. So that tells us how much the tax rate is going to go up for every dollar we make. So in this case, 0.06 is our rate of change. It tells us our tax rate per dollar. Just like how in this first one, 21 told us our price per customer. It told us how much the cost was going to be for every customer we add, right? Let's look at one more example. So this last one says that it's telling us that the distance, right? Distance equals 20 times the time traveled. So that means 20, since it's multiplied by t, is the coefficient, right? Or rate of change. So what that tells us is that for every hour, 20 tells us how far we can go, right? So for every 1 hour that the cyclist goes, they'll go 20 miles, right? So in this case, 20 is a rate of change. It's a speed, right? It's average speed, miles per hour. So what we're really trying to get at here is that when there's a lot of equations that look like this, they have one variable equals another variable times a number. They have one variable equals another variable times a number. And that number that's being multiplied is the rate of change, because it tells us how much changing this is going to change this. If we picked a different number here, we would end up with a different relationship. So there are a few example problems in the homework. In fact, there's really 3. I want to look at one together, and then the other 2 you're going to do on Desmos on your own. So this first one we're going to do, let's bring it up the side here. All right, so this first one we're going to do, it says, let's say after the bike tour, the riders put their bikes into a van and then head back to Atlantic City. Complete the rate, sorry, I'm just going to make this half the page. Complete the rate table on the left to show how distance depends on time for different average speeds. So we're trying to fill in this table for how far the van would go for different times depending on how fast they're going. So let's do one column together, and then we'll see if we can complete the other ones. So this tells us that in 0 hours, we can go 0 miles per hour if we're going 50 miles an hour. In 1 hour, we go 50. In 2 hours, we go 100. So for every hour, we go 50 miles, right? So I'm going to go in 3 hours, we would go 50 times 3 equals 150 miles. In 4 hours, it would be 50 times 4 to get 200 miles. So this second column then, we'd have to multiply, we're trying to figure out if we go 55 miles per hour, well, in 0 hours, we would go 0 miles, right? If we go 55 miles per hour, we would go 55 miles in 1 hour. In 2 hours, we'd be able to go twice as far. So we're going to do 55 times 2, or 110. And in 4 hours, we would go 4 times 55. So I don't know how to do that in my head, so I'm going to pull up my calculator at the top of the screen and do 55 times 4, and I got 220. Okay, and we got one more to do. And I think you could probably do this without me, so I'm just going to do it so we can move on. So I'm multiplying the speed in miles per hour by how many hours we're going, right? So if we're going 60 miles an hour, in 2 hours, you can go 60 times 2, 120 miles. In 3, it would be 60 times 3, or 180 miles. So what rule am I using? Well, I multiplied the number of, the number of hours traveled by the speed to find how many miles they would go. There are probably other ways to do this. I imagine some people would say, well, you could just add another 60 for every hour. You could do it by adding, a lot of different ways. So this is asking us to write an equation to show how distance and time are related for each speed. So we're going back to a little bit of what we did on Monday, which is writing equations. So it looks like the table's all filled out except for there's a column at the bottom to write an equation for each one. It says use the rule that you found on the last slide to write an equation to show how distance d and time t are related for travel at each speed. So let's go back to the last slide. We said that we multiplied the number of hours by the speed to find how many miles they would go. So we're supposed to use that rule. So we said that to find the distance d, we multiplied the speed, which I guess in this case is 50 miles an hour for that first column, times t, the number of hours. And here, pause and see if you can do this one for yourself, and then come back. Similarly, we're multiplying the speed, which for this column is 55 miles an hour, times t for the number of hours we go. And then lastly, 60, since that's the speed, times t. So my equation for each one is d equals 50t, d equals 55t, and d equals 60t, and we just change the coefficient because we're changing it based on what the speed is, because that tells us how far we can go. So it's asking us now to graph the data from our table on the coordinate grid. So let's see. So it says to use purple for the 50 mile an hour graph, so I'm going to graph 0, 0, okay, 150, 2, 100, 3, 150, 4, 200, okay. And in this case, I guess it does make sense to connect the dots because, to me personally it does, because you can figure out how far you're going in between the hours, which is kind of nice. All right, let's do, it says use green for the data for 55 miles an hour. Okay. Well, in 1 hour, you can go 55, which is, we're going to draw 0, 0. 55 is pretty close to 50. I'm going to say it's like right there. And then 110, which is, I think, right there on that line. Okay. 165, which is a little bit trickier. I think it's like right there. And then 220, which I think is like up there. Yeah, that seems pretty close to me. And I'm just going to draw a straight line between those. Whoa, that's not bad. I guess it's a good fit. All right, lastly, use blue for the data for 60 miles an hour. Okay. 60 would be right here. Oops, I'm going to get my good pen. There we go. 120. 180, which I think would be right there. Oh, maybe a little bit above there. And then 240, which should be pretty close to like up there. And then I'm going to take my line and just draw a line up there. All right. Moving on to the next slide. That was just graphing points. That I feel pretty confident with. Oh, it says, what patterns do I notice between the three different speeds? Well, I notice they're all straight lines. That's one thing I notice. The fastest speed data had the steepest line pattern compared to the slower ones. Because I'm looking at this saying like, well, the one that's the steepest, this one, is 60 miles an hour, and the ones that were less steep were the slower ones. So I said that the fastest one had the steepest pattern compared to the other ones. But I will say they're all increasing, right? Because they're both, when the time goes up, the distance goes up, so they're all increasing patterns. And I think they're all linear, meaning that we can draw a line. They go up by the same amount each time. So there might be other patterns that I'm missing, but those are the ones I thought of. Okay, so this next part says, what does the coefficient mean in these situations? So remember that Theo came up with equations to show how the distance changes over time for each speed. So for example, the equation Theo made for how distance changes over time for a van going 50 miles an hour is d equals 50d, which is nice because that's the same thing I had, so that makes me think I'm on the right path. In this equation, 50 is the coefficient, the number being multiplied by a variable. Okay, I agree with that, right? We said that over here in our other screen, that, remember how we said we're looking at equations like y equals mx plus b? Well, this one's pretty similar to that. It's just d equals 50t. So instead of a y, it's d instead of m, it's 50. Instead of t, it's x, right? So, or instead of x, it's t. So that makes me feel like I'm on the right track. Like y equals mx plus b, or mx, but instead it's just d equals 50t. So yeah, that's the coefficient, or we said the rate of change, right? Okay, so Theo says that the coefficient in each equation in this table is the average speed that the van is going. Is he correct? Try this one for yourself and see if we agree. But I think I agree that 50 is the coefficient is the rate of change, meaning it tells us how far the van goes in an hour, and that is the speed of the van. So like if I told you how far the van can go in an hour, like how many miles per hour, that's the same as the speed. So, and you might also notice that the coefficient here is always equal to the speed, right? So like d equals 50t down here, whoops, there we go. You might notice that, it's always equal to the speed up there, 50, 55, and 60. So this is a great example of like what we said from our notes of, let's see if I can get our notes in one place. For some reason, it doesn't want to let me scroll today on my notes, which is, there we go, better. There we go. It's a good example like from our notes that in an equation like this, when it has this y equals mx form, the coefficient is the rate of change, right? It tells us how much one variable is going to change when the other one changes. In fact, let's actually add that to our notes, because we just put rate of change without explaining it. So maybe we should add that to our notes. So let me slide these over and try adding that to our notes. So let's move our example down a little bit. And I'm just going to take my eraser and erase these two little lines. That when we use the word rate of change means how much one variable changes when we change the other. So for example, how much the distance travels when we change the time, or how much the cost changes when we change the number of customers, or how much does the tax rate change if we change the numbers. How much does your tax change when you change the price, or how much does your distance change when you change how long you ride for, right? So that coefficient is the rate of change, which is how much one variable changes when we change the other. So we might see things like speeds or prices. Those are common rates of change. All right, so there's two more parts to this first question that we're going to go over. One of them, it says, how far would the van travel in 6 hours? And it's asking us to figure that out from either the table, the graph that we made, or the equation that we just figured out. So you can fill in this table on yours as well. I think based on the pattern that I see, that distance equals 50 times the time. In 6 hours, it would be 50 times 6, which would be, I think, 300 miles, or 55 times 6, or 60 times 6. So I figured out the distances by using the equation that told me that distance equals the speed times the time in hours. Cool. This one is the last part of the first question. So from here on out, I'm just going to kind of review the assignment for you, and you're going to do it on your own. And you can do it with us during our live class too if you're there. So there's a practice problem about trying to figure out how much it's going to cost you to have a certain amount of text messages on your phone. And then lastly, there's some problems at the end that are kind of more like working with equations that are in this y equals mx form. And then at the end, it's just going to ask you to do a kind of a confidence check. So how confident do you feel with using tables, graphs, and equations that are in this y equals mx form? Are you confident? Are you unsure? And then maybe what you explain a little bit more about what you're confident about and what you're unsure about. I'll post the notes to Classroom as well if they're helpful, but you should take your own in your notebook too. And again, if you have any questions, just email me and let me know. All right, thanks.